So the second part of this CFD tutorial is going to be about creating and perfecting our mesh for our geometry so that we can simulate it correctly and more accurately in CFD. Because the better the mesh, the more accurate your results are going to be. So that we do that, once we've done our geometry prep, we'll see this green tick here. We're going to go ahead and select Fluent with Fluent Meshing and drag that in to here. And then we're going to right click on Mesh and go to Edit, and it'll bring up this window right here, which is a Fluent launcher window. We want to click Double Precision. That just improves our mesh and our runtime a little bit. And then in meshing processes and solver processes, we're going to select and type in the number of cores or CPUs that we have on our machine. So in my case, that's 8. And then hit Start. So selecting more cores is obviously going to improve the speed of certain processes like the meshing and the solving, because it'll be able to split the computation between multiple cores. But if you only have one, that'll still work. It'll just be a bit slower. So it'll bring us this page right here, at which point we don't actually have our geometry in. You see everything's grayed out in the outline view, and nothing is here in the graphics window. So to change that, we go to File, Import, and then select CAD. It's going to bring up this file right here. Make sure the length unit is in millimeters, because that's how we work with all of our parts. And then browse for the file you're looking for. So in my case, I saved it to the desktop last time. So the way I can go back to find it, if I go to desktop, and then you'll see in the desktop, there's a folder called CFD tutorial under dash files. Because I called my workbench file CFD tutorial, it has automatically created this folder right here in the exact same directory. So if I double click it, it has a bunch of stuff in it. We want DP0, which is design point 0, because we haven't created any other design points. So double click that. And then there should be a folder called geom, which is the geometry we just created in Design Modeler. So double click that. DM means Design Modeler, so double click that. And there it is. That file right there, geom.agdb, is exactly the file we want to import into here. So click that and click OK, and then click Import. It may take a second, but the result you'll see will be the geometry that we just created in Design Modeler will pop up here in the graphics window. And on the left-hand side here with the outline view, you'll be able to see all of the name selections we created, the bodies we created, etc. So there it is. There's our box. And the way we can check if it's correct, if we open up the plus icon on geometry objects and then go through, we'll see we have the inner boy, which we created, and the outer boy. And if we open up face zone labels under the outer boy, we'll see all of our name selections. It's very important that all of these name selections are associated under the outer BOI and not the inner BOI, because the inner BOI isn't actually going to be simulated at all. It's just a reference for our mesh. But the outer BOI, yes, we do want that to have all of our name selections. And then if we want to see if they're correct, if we select all of, say, these ones, and the trails and the gurney, right click and go to draw. And if we zoom in, we'll see that those are indeed the parts that we wanted simulated. And that's the CAD that we initially imported. So we know that that's correct. Okay, so the UI is going to look slightly different all of a sudden. That's just because I switched over to a slightly more powerful machine that actually runs Fluent in Linux. So the principles are going to be the same, but the outlook, just the look of it, is going to be slightly different. But you'll be able to follow along nonetheless. So once we've opened up our CAD into the Fluent mesher, and it's going to look something like this, we have our outline where we can see all of our things. We then want to set the sizes for our meshing. So the first thing we do is we create a surface mesh of the 3D model. It's going to create a 2D mesh on all of the surfaces, like the outer box and all of our rear wing surfaces. And we set sizes for each different face. So we're going to tell the system, like the inlet, we're going to want it to be a certain size of mesh, whereas the rear wing, obviously, we're going to go smaller and smaller as we get closer. So the way we do that is if we go to Model in the outline view, right-click, go to Sizing, and then Scoped. And this window right here is where we tell it what sizing mesh to put on what faces. So we're going to begin, because the reason we created the body of influence is this is why. We're going to begin by setting general sizes for the body of influences. So that's going to affect all of the mesh cells inside each of our respecting inner and outer BOIs. So the first one we're going to add is we go to Type, select BOI, which is body of influence. And we'll start with the outer one first. So we'll name it something like outer BOI. This name has nothing to do with any of the meshes. It's just purely for this list right here. So you can name it whatever you want. We're going to set the outer BOI to be a maximum size of 250 for each cell inside. The minimum is grayed out because it doesn't apply for a BOI. And then under object faces and edges, we're going to go into selections and we're going to select outer BOI. So right now, both of them are selected. So we'll select both. And then we just want to select outer BOI. We want to deselect inner BOI. So make sure that that's the only one that's highlighted and then hit OK. And so once we've done that, we can create our first scoped sizing. So we hit create and you'll see it gets added to this list after this. Yep. So that's going to say, because the minimum is less than the global minimum, do you want to update the global sizes? Sure. We keep saying yes whenever that window pops up, but it doesn't really matter that much. So you can see it's now been added to the left-hand side as a scoped sizing right there. So next we can just add another one, but this time we'll make it the inner BOI. So inner BOI, we'll set this time a max of 100 because we want to get smaller and smaller cells the closer we get to the rear wing. And then instead of selections, under here, instead of under BOI, we want to go to inner BOI. So, okay, and then we can create this one as well. There we go. Now we have our 2 BOI sizing. So that's the only BOIs we created in the geometry. So that's the only ones we have to do in here in the scope sizing. Next, we can start with the airfoils. So those will be under curvature because those are curved surfaces. So we want to make sure our type is curvature. We'll select element, we'll name it element 1. And then what we want to do is set the minimum size of any cell on the surface to be 0.1, while the maximum is going to be 5. And the normal angle, which is the angle between any 2 adjacent cells, has to be no greater than this number right here. We're going to set it to 2, which means that it's going to have a nice smooth curvature to capture the leading edge, especially of each airfoil. If we set this to really, really high, it could simplify the leading edge to be quite jagged, and that's not what we want. So we want to make sure this is quite small, especially for airfoils, so it's really important. And then we're going to change the scope. We don't want to scope to object faces and edges anymore. Now we want to scope to face zones. And so then if we browse through the face zones, we can see all of the name selections that we set previously in our CAD. So we can select this button right here to deselect all of them, and then just click element 1 curve, because that's the one we want to scope to right now. So we'll set these and then hit create. And that's another scope sizing. Now this is going to be, again, scope sizing. The minimum is less than the global minimum size. You want to update yes. Not sure why it moved that. Let's bring that back. There we go. Now we'll make the next curvature, which is for element 2. We're going to leave the same parameters, but now just select E2 curve. There we go. Hit OK. And create. And lastly, E3, so element 3. Again, same parameters, but select E3 and deselect E2 and create. All right, so that's our curvature done. Next, let's go ahead and do our gurney flap. So that's that really small tab at the very back. And so we're going to want very, very small, fine mesh right there around that area. So instead of curvature now, because the gurney flap isn't curved, we're going to set this to hard. Now, a type hard means that it gives... on the whole surface you select, it gives it a size mesh to sort of look for, and then it forces that whole surface to be of that size. So, for example, if you set it to 0.1, every single cell in that surface or in that region will be 0.1. There's no leeway on that. And because our trail is very, very small, we actually want to set that to 0.01. And no, sorry, 1, not 0.01, just 1. Which means every single cell is going to be 1 thickness or width or whatever dimension it is. It just has to be 1. So we'll name that gurney. Oh. And instead of E3 curve, we're now going to select gurney and then hit OK. And that's another one we can say create. All right. So now we've done the gurney. Let's move on to the big end plate faces that we have. So those are going to be under soft. So soft, similarly to hard, but not exactly the same, you're going to give it a size that it's going to aim for, but instead of forcing each cell to be that size is going to be a maximum. So no cell will be able to be bigger than whatever size you set, but it can be smaller to any degree, which is good for a really big really big surface like that, like the end plates, because you don't want very, very small mesh cells all over that face. So we're going to set that to be 10, which means the biggest cell it could be on the end plate is 10, but it's going to grow smaller and smaller as it gets closer to more details, like the edge of the end plate or the airfoils. And again, we'll deselect gurney from here and select end plate soft, which is what we named our flat surfaces. And then we'll name it soft. I don't think it really matters. And then hit create. All right, so all that's left now is the trailing edges, the trails, the one we named right here, and the end plate prox, which is that really thin, I guess, layer of edges or faces that is around the end plate. And those are both going to be under the proximity type. Proximity type is a little bit complicated. Essentially, when you have very, very thin faces, like the trailing edges or the edge of the end plate, you want to set a number that will tell it how many cells to put in between one edge and the next of that really thin. So if you imagine a very thin strip, and then we say we want 3 cells wide inside that strip, so that the whole length of that strip is going to have 3 cells top to bottom. And that's what this cells per gap is right here. So we want to set that to 3. We want to set the maximum cell size anywhere along the proximity to 2, and the minimum, this is where it gets very small, to 0.01. This gives it good freedom to basically do whatever it wants inside that gap, as long as it fits 3 cells in it. And then we're going to take face boundary, because that's the boundary within which we want it to set this number, is a face boundary. And then we will deselect end plate soft and select the trail, so the trailing edges. Okay, and name this something like trails. And then hit create. It's going to say, yep, scope sizing minimum is less than minimum global. So just hit yes again and updates that minimum global. Finally, the very, very last one is going to be the end plate prox. So we can just type in there. We're going to have the same settings, face boundary again, but instead of trails, we're going to set end plate prox and hit OK. And then create. Now, the very last thing, which is optional, but if you want to, you can change the global maximum to match the outer boy maximum, which is 250, but you don't actually have to, because it's going to set it anyway because you set it as the outer BOI. But it's maybe good practice just to set that number as well. Now that we have all of this list, then we're going to create what's called a sizing field. So if we hit compute down here, it's going to compute all of these sizes relevant to our geometry, and then output a size field which we can then use to mesh our part. So we'll hit compute. This might take a second, depending on how big your geometry is, how small you made these size fields, and also how many proximity types you have, because those are the most computationally heavy. So we can check the progress in the console, and it'll look something like that. And there we go, it's done. But that's because this is a 24 processing machine that I'm using on P. So it might take a bit longer if you're using a laptop. Don't worry about it, as long as it gets done eventually. And then we can hit close. Now, you won't see anything different in the graphics window. It hasn't actually done anything. All it's done is basically created an internal file with which we can now use the meshing function with. So to mesh, we're going to go into the outer BOI, because that's the actual box we want to mesh. Right-click, and then go to remesh. So if we click remesh, you'll get this window. We want to target individually. I'm not going to lie, I don't know exactly why, but it doesn't work properly with collectively. So we're just going to do it individually and then hit OK. Now, this might take a second for sure, but we will wait it out. And what you will see afterwards is all of the 2D mesh that I'll show you in a second. Okay, so once it's finished, Again, you'll see graphics, nothing has actually changed yet, but you can see we've now added a new object under here. Under mesh objects, it'll be called outer BOI dash mesh. If we open it up, you'll see it still has those same face zone labels, but this is now a mesh object as opposed to a geometry object. And we'll be able to see this if we right click and hit draw. It'll look like the same box, but if we then go to display and face edges, if we tick this, we can now see all of the cells that it has created in our mesh. And this is what we've managed to do so far. So you can see the cells that might look fairly small, but they get really, really small around the rear wing itself. So if I just go ahead and draw the airfoils, right click, draw, and then we'll fit it to the window. I think that's here. Yep. There you go. You can see you can barely make out that there's actually lines in there. It just looks all black, and that's just because there's so many cells close together that it's hard to make them out. But there you go. That's a sign of a good mesh, firstly. But it's not quite perfect yet. We actually need to go ahead and improve the mesh because it's not enough just to set a bunch of sizings and call it a day. So the way we go ahead and improve it, if we right-click Outer BOI Mesh, and then go to Diagnostics, Connectivity and Quality. So this window right here is basically where we diagnose how good our mesh is and take steps to improve it. So this is a bunch of error fixes that we can do. And then if we go into quality, this is a bunch of quality improvements we can do. So we'll start with a couple of error fixes. Again, I'm just going to go through this as a process because that's what I found works 99% of the time. But if you end up finding a better way to improve this mesh that's a bit faster, feel free to do that. So the first thing we're going to do is try and see if there's any free faces and stitch them together. So we'll hit mark on free faces to see how many we have, if any. We have 168. So I'm going to go ahead and click stitch and then apply for all. All of these processes might take a second. They'll take quite a while if they have a big mesh, especially like a full car. Then we'll go ahead and move on to the multi. See if there's any multi faces. Mark any of those. There's none, which is great. And then finally, we'll just check the duplicate edges real quick. Mark to see if there's any. And there isn't. Perfect. So those are the three main errors we're going to fix at the beginning. But now we're going to go into the quality. And this is the big thing. So there is one diagnostic tool, which is going to be very useful to us, which is called skewness, which is a measure of how, I guess, good any mesh cell is. So the nicer the shape, like the more equilateral the triangle or the nicer the square, the better that mesh cell is going to be because it can be easier for the computer to solve equations on its boundaries. If the mesh is really skewed, so if we have a triangle that's very, very long and thin, then it's going to be much more difficult for the computer to solve all of the equations necessary for that cell. So we want to make sure that our skewness is quite low. We want to aim for definitely below 0.8. But the lower we can go, the better. And it's between a scale of 0 to 1. So now this is another process that we're just gonna show you how to do. So first, we're gonna highlight any cells that are above a skewness of 0.95. We're gonna hit mark, and there will definitely be some. There's always some, but they're very easily cleared. Now 711 might look like a lot, but don't worry, it's not. First thing we're gonna do is go general improve, and apply for all. That'll solve a good majority of those 711, but not all of them. But we'll come back later and then solve them completely. Once it's finished, we then move down to 0.9 and do the same procedure. Hit mark and then hit general improve, apply for all. And we'll keep doing this until we're down to 0.7. So once we've hit 0.7. So I'll speed this up a little bit and then I'll show you what happens next. Okay, so once we repeated this procedure all the way down to 0.7, we can then go ahead and hit mark again to see how many cells are left with a skewness of above 0.7. And we'll see there's actually 97 left. The way we can now fix this is if we go back up to 0.95, hit mark, you'll see we have 5 above 0.95. And now instead of generally improve, we're going to hit collapse. This is a different fix. So instead of just generally improving the cells around it, so trying shifting around the nodes, this is actually going to collapse those ugly, very skewed cells and just close that boundary with the adjacent cells. And this is usually much more effective at removing the last few skewed cells. So we're going to head and make sure preserve boundary is ticked so that it doesn't actually affect our geometry boundary. And then hit apply for all. And we're going to repeat this procedure all the way down to 0.7 like we did before, but now with collapse. So 0.9, mark, and apply for all. And if you see that this doesn't happen to be working, so say if we hit mark again and we see that there's a number other than 0 here, what we can do is increase the iterations to something like 10 so that it iterates over and over again, collapsing more and more cells so that it's more likely to complete what we want it to do. But I'll keep going. 0.85, mark, and collapse. Okay, so once we repeated the cycle with the collapse instead of generate improve all the way down to 0.7, we can see how many are left that are above 0.7. If we're lucky, this is 0. But if not, we can either keep repeating the collapse, or what we can do, and this is just good practice, we go ahead and now smooth anything above 0.7. Now what this does is, because we've now generally improved quite a few times and collapsed quite a few times, it may have shifted around quite a few cells that we don't know about. And by smoothing it out, it kind of resets any bad movements that the computer did. And smoothing takes the longest of these operations, but it is worthwhile. Even if it might re-increase the maximum skewness of any cell, it'll be worth it in the long run, especially when you get into that 3D mesh. You do want quite a nice smooth 2D mesh. So we'll hit apply for all for the smooth, and you'll see this does take quite some time. All right, once that's finished, we can hit mark, see if it's increased the number, which it most likely will have. If not, you're lucky, but it most likely will have. In this case, we were lucky. It's actually gone down to 0 cells above 0.7. But we could be happy with 0.7. I like to go all the way down to 0.5. So if we repeat that whole process of marking, generally improving, apply for all the way down to 0.5, we'll get an even better mesh. So I'll apply that. And I'll just speed this up again. All right, once we've gone down all the way to 0.5, we'll hit mark, see if we have any more that are above 0.5. If we do, we'll then go back up to 0.765. And instead of general improving, we'll go through the collapse procedure again, all the way back down to 0.5. And we will see after that if there's any left that are above 0.5. And we'll mark it once more to see how many we have left. In our case, we have one face that has a skewness above 0.5. So that's pretty good. It depends what the maximum skewness of that face actually is. And to find out, we can go to summary. If we hit summary down here, and then we'll go to console, we'll see the maximum skewness is 0.5699. Now, that's very, very good. We don't need to worry. And we know there's only one face that has that skewness right there. Everything else is below 0.5. So that's more than good enough for our quality. And so the last thing we want to do is just double check the errors again, just in case us moving the mesh around has screwed anything up. So go ahead and mark any free faces, which hopefully there shouldn't be any. Go ahead and mark any multi-faces. If any of these numbers come out as not 0, then there is an issue, and it's most likely that something went wrong with the fixing of the mesh, and you may have to start again with the meshing procedure, because it's very difficult to come back from once you've tried fixing the geometry to then try and fix it again to like clog up any of these errors. But it looks like we're good. The last time we'll check is duplicate. And if this is also 0, these are more often than not always 0. So looks like we're good. So we'll hit summary one more time just to get a final summary of our 2D mesh. Close out of this. And we can see this console window is a bit weird. There we go. We have 0 free faces, 0 multi-faces, 0 duplicate faces, 0 skewed faces, and this is our maximum skewness, which is excellent. So once we've done that, we can now move ahead into the 3D mesh. I would say if this maximum skewness is below 0. For a simple rear wing, below 0.75, you're good. Anything above that, I would question, and definitely if it's anything above 0.85, I would try and fix. So this is very, very good. All right, so to make the 3D mesh, we now go into volumetric regions down here, right-click, and compute. Basically, that essentially pinpoints where our 3D mesh is supposed to go. So we have our box, and it's going to basically compute where our fluid needs to go. So it needs to go inside the box and around the rear wing, and that's what it's done. And if this does it successfully without any errors, it means that your mesh is hole-free. Obviously, we don't want any holes in our mesh, but if there is a hole, you got to start again because it's almost, in my experience, very difficult and almost impossible to fix holes. So there it is. There's our volumetric region. We're going to right-click on it, make sure that it's change type set to fluid because we want fluid running through it. So hit that. And finally, we're ready to create our 3D mesh. So the way we can do that is if we go to this one and then this one, cell zones, right click on cell zones and go to auto mesh. It's going to bring up this window, which looks like it has a lot of options, but I'll talk you through the ones we need to do. So firstly, what do we want to mesh? We want to mesh this mesh object that we created right here. So it's outerboy.mesh. These don't matter because they don't have any solid or dead zones. If we did, we could uncheck these to make sure that those are deleted. We don't want those in our final thing, but these for us don't matter. Boundary layers. Now this is where we can grow our boundary layer cells around our part. This is very important. We want to make sure this is set to scoped, and we'll go ahead and set what we need to set. So we only need one scoped prism, and that's just going to select the entire of the rear wing faces. So we'll name it, I don't know, boundary. Our offset method is going to be last ratio. This is how the boundary is going to grow. And our first height, if you remember from the 2D CFD tutorial, this is something you look up depending on your geometry. For this, our first layer height for this particular rear wing is going to be 0.0158. That's millimeters right there. And we want 12 layers. And our last percent is going to be 20. So that's just this last percent right here, and this last ratio method basically tells the system how thick the last cell of the boundary layer should be relative to the whole boundary. So in this case, it's going to be 1/5 of the whole boundary. Finally, we need to select where the boundary needs to grow. So it's going to scope to the fluid regions, but it's going to grow on selected face zones. So we don't want it growing on like the inlet or the outlet. We only want it growing on our actual geometry. So that's going to be our E1 curve, E2 curve, E3 curve, our end plates, our gurney, not the inlet, not the outlet, not the slip-ons, and not the symmetry, but yes, the trails. We're going to hit OK and create. And there we go. That's created the only one we actually need for our scope prisms. But if we go ahead into growth options, we want to make sure that the stair-stepping method right here, instead of this quality, is going to be set to skewness. And we don't want anything above 0.9 in the stair-stepping threshold. And hit apply. That'll just help reduce the skewness of the 3D mesh. So we'll close that and close out of that. So that's the boundary layer done. Next, we want to select polyhex core as our volume fill. So this is the shape of the cells that are going to fill our 3D space. There's 4 different types, but polyhex core is the easiest to conform to difficult shapes, and for difficult shapes, the fastest to solve. So we'll hit polyhex core. It's going to gray out a bunch of options, which is very good for us. But we're going to click set in here, and we're going to click avoid 1 to 8 cell jump in hex core. So that just means that it's never going to have a cell next to a cell where the growth rate between one and the next is 8 times or 1/8. So no cell is going to be greater than 8 times bigger or smaller than the cell next to it. That's a bit complicated, but I think that makes sense. Basically, it just means that you won't have very quickly growing adjacent cells, which is good. So hit apply, and then hit close. And finally, you do want to auto partition. That just means that your meshing procedure is going to be much, much faster because it's going to split it among all the cores available. But you also want to merge cell zones within regions. That just means that if you have multiple regions, for us, this isn't going to matter. If you have multiple fluid regions, it's going to merge those so that the fluid can flow from one to the next without any problems. Because if you don't merge them, then you'll have 2 separate ones. You have to set an interface between them, and that gets a bit complicated. Not that you'll be using it much, but make sure to always tick it to avoid any problems. And after that, we are ready to mesh. So we'll hit apply, and then we can hit mesh. It's going to come up with a message that tells us, do you want to proceed with parallel meshing, which is the quick version of meshing. It will remove some features afterwards that you won't be able to do if you parallel meshed, but for us, that's fine. It's not any features that we care about particularly. So we'll go ahead and yes, and it's going to start meshing. This will definitely take the longest time out of any meshing procedure. So I'm just going to cut to when this is finished. Okay, once the 3D mesh procedure is finished, we need to go ahead and just make sure that everything went correctly or that the skewness is good, and then we can go ahead and start solving. So we'll close this window. You'll see a new object has been created under cell zones, which is the outer BOI cell. This means there's now a 3D mesh. So to check our skewness, we want to go to report, quality measure, and we're going to change the quality measure to skewness. By default, it's inverse orthogonal quality. We just want to set it to skewness and equilateral skewness. So apply, and then close. Now, we'll right-click outer BOI and hit summary. This may take a second to load, but it'll show us a summary of our cell zone mesh. And initially, it may look bad, but we will go ahead and fix that. There's a very easy method to fix it. So we can see our maximum quality, so our maximum skewness is 0.8988, which is below the required 0.9. So we would already be good at this stage. But I'm going to show you how to fix it if that isn't the case. But yeah, anything below 0.9 is good to go in the 3D mesh. In the 2D, remember, you want it as low as possible. In 3D, anything below 0.9 is good to go. And the reason this is so low the first time round in the 3D is because our 2D mesh was so good. So if you spend time improving the 2D mesh, you'll have no problems with the 3D mesh. But let's say that our maximum quality is above 0.9. What do? We'll right-click on this cell zone again, go to Auto Node Move. Now, we basically set the limit of how high do we want our max skewness to be. And you want to do this in steps like we did for the 2D. So we can start something like 0.95. It'll have automatically selected the mesh, so don't click anything in here. How many iterations you want it to do before it stops trying to fix. So we'll say something like 10. And then we'll quality measure. We want to select, make sure it's on skewness still. And then hit apply. And that's going to go through 10 iterations of trying to move nodes around such that the maximum skewness falls below 0.95. If I do it here, it won't do anything because the max skewness is already below that. So we'll hit apply and you'll see that it says no cell above threshold. And then you step down again. I would suggest if you have a very, very high maximum skewness, go down in steps of 0.01. So like start at 9.9, then go 9.8, 9.7, etc. We can try and see what would happen. We'll go to 0.85, and we'll see how much it can fix. So we'll apply. You'll see we have 12,000 cells above 0.85. Now it'll do 10 iterations trying to move things around, and we'll see how low we can get. But again, this isn't necessary. We just need to be below 0.9. So we'll wait. This might take a second as well, because now the mesh is 3D. It's much, much heavier computationally to do anything. So this procedure that you're doing here in 3D takes a lot longer, which is why it's good to just get it done in the 2D and not have to worry about it. But we'll wait here. We'll see how much it improves. You can see after the first iteration, it dropped down to 0.877, and then it's going to keep going down very, very slowly for all 10 iterations. But yeah, so that's how you'd improve the 3D mesh. We are more than happy with this. Maximum skewness is now 0.866. That's very, very good. So now the only thing left to do is to go into the solution and actually solve our case. So yeah, the mesh is complete. It's good practice now, instead of just going straight to the solution, to actually save our mesh. So if we go to File and then Write Mesh, basically saves a backup. So yeah, we'll save it as whatever. Get rid of so this GZ extension right here, which sometimes it might want to save as, is essentially a zip. So the file size is going to be smaller, but it's going to take much longer to open. So if you have a lot of space on the computer or hard drive, get rid of this .gz because it will speed things up. If you're slightly more tight for space, you can keep that gz. I'm just going to get rid of it. And I'm going to save it as, geom.msh. So hit OK. Take a second. It'll also take a lot longer to save if you are zipping it, because it has to go through the zipping procedure as well as the saving procedure. And I'll show you how big the file actually is for a mesh like this, so you'll get an idea of how much space you might need. Because the mesh files are probably one of the largest. There we go, it's done. So let's see how big that was. So we'll go to Home. Ignore all those files. So our mesh is 3.2 gigabytes, and that's only for a single half a rear wing. So you can imagine how big it would be for an entire car, or even just like, I mean, if we did the whole rear wing, that's going to be 6 gigabytes. So we're really saving quite a lot of space by cutting it in half. All right, once we've saved that, we are ready to just go to the solution and start solving. So we'll hit switch to solution. Ensure that the mesh is valid for you. So we know that the mesh is because we checked the maximum skewness. So we'll hit yes. And then it'll shift us to the solution. So it'll open up a new window of Fluent. So it'll look slightly different. All right, once this comes up, so this file, right, you'll have a task page in the middle. See, if you go to graphics, you won't see anything because you haven't drawn anything yet. And all of these tabs up here have changed, as have these. So once you see this, if you go into the boundary conditions and cell zone conditions, you should see all of your name selections that we have right here. If that's the case, then we're ready to start solving.